Kimi K3, Open Frontier Intelligence. We're jumping straight into the deep end today because this release is just an absolute monster.
Yeah, it really is.
So here is the dense, 60-second download for the ML engineers and AI researchers tuning in. Kimi K3 is an open-weights 2.8 trillion parameter mixture of experts model. It runs 104 billion active parameters with a 1 million token context window.
The huge numbers.
Right. And the paper claims a 2.5x scaling efficiency gain over Kimi K2. How? By basically ditching pure softmax for a hybrid architecture that mixes Kimi Delta Attention, or KDA, with gated MLA. It bypasses traditional depth bottlenecks using block attention residuals and stabilizes the highly sparse 896 expert latent mode design using, bounded activations.
Which is super clever.
Yeah. Post-training is heavily focused on multi-effort reinforcement learning across agentic encoding domains. The bottom line here is it sets a new open weights frontier. It trails only the top proprietary models like Claude Feeble 5 and GPT 5.6 Sol, but it consistently beats Claude Opus 4.8, GPT 5.5, and GLM 5.2, all while maintaining extreme cost efficiency.
Yeah, that efficiency is key. Welcome to AI Paperslop, by the way. I think looking at the current open source ecosystem, most of the recent progress we've seen has been, purely on the second axis of scaling.
Like the post-training side.
Exactly. We've seen a lot of test time compute and RL just kind of layered over the exact same 1 trillion parameter class foundations. But Kimi K3 is fundamentally different. It pushes both the base architecture and the post-training axes to the absolute limit simultaneously.
So the mission for our session today, for our deep dive into this paper, is to dissect exactly how the Kimi team achieved these crazy scaling efficiencies. We're going to unpack the hybrid attention math, the CU-GLU activation bounds, the massive MoonEP training infrastructure, and of course that million token RL sandboxing that makes this 2.8 trillion parameter model actually tick.
Right, because if you're trying to push 1 million tokens through a model efficiently without, literally melting your silicon, you have to fundamentally rethink the sequence dimension.
You can't just brute force it.
No, standard transformers rely on softmax attention, which we know scales quadratically. Every new token has to look back at every single previous token. At 1 million tokens, the math just breaks your hardware. So Kimi K3 shifts to a hybrid token mixing approach.
They use a 3-to-1 ratio, right?
Yeah.
Like in every architectural block, you get 3 KDA Kimi Delta Attention layers, followed by 1 gated multi-head latent attention, or MLA layer.
Yep, 3-to-1. And that KDA gives you this recurrent, chunk-wise linear attention, which scales linearly and is highly, highly efficient.
It's fast.
Exactly. Then every fourth layer, the MLA acts as your unrestricted global content interaction.
But the mechanical fix inside those KDA layers is what really unlocks this model, I think, because in previous iterations of linear attention, a massive numerical bottleneck was the unbounded reciprocal decay in finite precision.
Oh yeah, that was a huge headache. When you compute linear attention recurrently over chunks of text, you multiply retention factors, which are basically values between 0 and 1. So by the time you get to the end of a really long sequence, that cumulative decay is an incredibly, incredibly tiny number.
Right, and to rescale the keys in a chunk, you have to divide by that cumulative decay. And in BF16, brain floating point 16, which most of these models train in dividing by a microscopically small number, just causes a massive overflow.
Yeah, the values just blow up past the dynamic range.
So to fix this, Kimi K3 changes how they parameterize that decay. They mathematically bound the log decay using a scaled sigmoid, and they put a hard floor on it at -5.
Which is such an elegant fix. Instead of the cumulative log decay just drifting toward negative infinity over a 16-token tile, it is physically locked between -80 and 0.
Which means the reciprocal rescaling factor stays completely within the safe limits of BF16. And I mean, the hardware implication of that is massive.
Massive. Because the math is bounded and stable, both the diagonal and off-diagonal tiles can be computed densely on the GPU's tensor cores. Yeah, you entirely eliminate that slow position pair diagonal path bottleneck that made older linear attention models so difficult to scale in the first place.
So unlocking the tensor cores allows for that linear scaling up to 1 million tokens. But what they do with positional encodings is just as radical. For the periodic MLA layers, they use no P, no positional encoding whatsoever.
Yeah, no P.
I have to push back on this no PE decision, though. Like, if you were building a 1 million token context window, wouldn't dropping explicit position data hurt the model's ability to understand long-range dependencies?
You'd think so.
I mean, losing rotary position embeddings, or ROPE, You'd think that would be a death sentence for context retrieval.
It actually solves one of the biggest headaches in context extension, believe it or not. If you've ever tried to scale context windows using standard ROP frequencies, you have to constantly interpolate or rescale those frequencies to handle sequence lengths the model hasn't seen before.
Right, using techniques like yarn or whatever.
Exactly. But by dropping explicit encodings in the MLA layers, the model is basically forced to rely entirely on the recurrent gating and decay mechanisms operating in the KDA layers to implicitly encode position and recency.
Oh, I see.
Yeah, because it's processing token by token, the positional context is just baked into the recurrent state. You can extrapolate to 1 million tokens naturally without retuning any frequencies.
That's fascinating. This 3-to-1 setup, it actually reminds me of human cognitive processing.
How so?
Well, the 3 KDA layers act like you're continuously updating short-term working memory, right? You're holding the immediate context token by token. Then every 4th layer, the MLA acts like your deep global memory retrieval, scanning the entire sequence for broad connections.
That is a really great analogy. Yeah, so that solves the sequence dimension bottleneck. But once you optimize the sequence, the data hits a wall at the depth dimension.
Right. Standard transformers rely on residual connections. You add the input of a layer to its output to help gradients flow.
But over 90-plus layers, that forces all prior information through a single linear bottleneck state.
And Kimi K3 replaces that with attention residuals, or ATNRS. Instead of just a linear accumulation, each layer can selectively attend to representations from all preceding layers using learned pseudo-queries.
Yep.
But let me stop you right there, though. If you are telling me layer 90 has to look at the representations of all 89 previous layers, the arithmetic overhead alone is like big O of L squared D.
Massive.
Yeah, if you were running pipeline parallelism across multiple GPUs, holding those dense activations across 90 layers will vaporize your VRAM instantly.
You're totally right, and that activation memory nightmare is exactly why they implement block attention residuals.
Okay, how does that work?
They partition the 93 total layers into 8 discrete blocks of 12 layers. Within a 12-layer block, they just use standard summation.
No more residuals.
Right. The cross-layer attention is only applied over those 8 block-level partial sums.
Okay. So that brings the memory and communication overhead down from L squared D to just big O of ND, where N is just those 8 blocks.
Exactly.
But even holding those 8 block representations for a massive batch size, that still seems heavy for pipeline parallelism.
It is, which is why they mitigate it using sequence parallelism during the prefill phase. They decompose the tensor parallel all reduce operation.
Walk me through that.
So instead of a standard all reduce, which, duplicates the full tensor across every GPU, they split it into a reduce scatter and an all gather. And they insert the intra-block kernel right between those collectives.
Oh, wow.
Yeah, the block representations for any given token are materialized on exactly one rank, not duplicated across the whole cluster. It drastically cuts down the memory traffic.
Okay, so we've cleared the sequence bottleneck with KDA and the depth bottleneck with block ATNRS.
Yeah.
Now we hit the width bottleneck. To hit 2.8 trillion parameters, they rely on a mixture of experts, or MoE architecture.
Yep, scaling up the width.
And they push it to extreme sparsity. We're talking 896 routed experts, activating just 16 per token, plus 2 shared experts. But operating at a 2.8T scale with that level of sparsity introduces, catastrophic activation explosion.
It really does. In a standard MoE, pushing data through the down projection, the expert feed-forward network, and then the up projection, it creates a chain of essentially 4 consecutive matrix multiplications.
Right.
When you scale that to nearly 3 trillion parameters, that ill-conditioned structure creates massive activation outliers. The values just multiply out of control.
And they fix this with C2 GLU,
right?
Sigmoid ton unit GLU.
Yeah.
Because standard SWI GLU activations are unbounded, which allows those outliers to just run rampant.
Yeah, CGUU applies a smooth, scaled ton cap to both branches of the activation function. It caps the gate branch at 4 and the up branch at 25.
So the absolute maximum possible output from that layer is strictly bounded at 100.
Okay.
It feels like installing a high-performance governor on a sports car engine. You keep the aggressive near-linear acceleration at low RPMs around 0, just like a swish activation, but you physically prevent the engine from revving past the red line of 100 and blowing up the sparse routing.
That's a perfect way to picture it. Bounding the worst case magnitude preserves the local gradient dynamics while ensuring stability. But, bounding the activations is really only half the battle. You still have 896 experts.
Right.
Balancing the load across nearly 1,000 experts without using auxiliary loss functions is notoriously difficult.
Because if you use auxiliary loss functions to force tokens into underused experts, it constantly fights the primary language modeling objective.
Yeah.
The model basically gets penalized for making the best linguistic choice just to satisfy an arbitrary balancing metric.
Exactly. It's a huge trade-off. So Kimi K3 bypasses auxiliary loss entirely by introducing quantile balancing, or QB.
Okay, what's QB?
Instead of a fixed-step sign update for the expert bias, QB uses a global histogram estimator. It dynamically adjusts the expert bias based on token margins across the entire global batch.
Wow, the whole batch.
Yeah. And because the histogram counts are additive, they can just perform a single all-reduce operation to sum the bins across all ranks.
Oh.
It mathematically guarantees that each expert gets its exact target load without ever interfering with the main training loss.
That is wild. Okay, so up to this point, we've essentially built a brutally efficient text architecture. But Kimi K3 isn't just a language model, right? It is natively multimodal. The vision encoder processes images and video right alongside text.
Natively, yeah.
And this is where the team booked a massive industry trend. Normally, if you're building a multimodal model, you initialize your vision encoder with a pre-trained contrastive model, like SIGLIP.
Right, that's standard practice.
But Kimi K3 dropped contrastive pre-training entirely. They trained their 400 million parameter MoonEP v2 from scratch using pure next token prediction.
They had to. Using a pre-trained contrastive encoder at a 3 trillion parameter scale caused severe gradient spikes and training instability when they attached it to the LLM.
But why? Why does contrastive pre-training fight with the language modeling objective so badly? Is it because a contrastive loss, like trying to match a whole image of a dog to the text string dog, favors broad global semantic understanding, whereas a language model fundamentally needs fine-grained token-by-token structural cues?
That is exactly it. Contrastive models collapse all the fine visual details into a single semantic vector.
Right.
When the LLM tries to extract structural information like, say, reading text on a sign in the background of an image or understanding spatial relationships between objects, it forces the vision gradients to wildly restructure those pre-trained contrastive weights.
It's fighting the pre-training.
Yes, that massive realignment is what causes the gradient spikes. By training MoonEP v2 from scratch on next token prediction, the visual representations are shaped natively by the structural needs of the LLM from step 1.
That makes so much sense.
Yeah, the gradients remain perfectly stable, and the crazy part is the final performance matched the contrastive baselines anyway.
So they didn't even lose anything.
Yeah.
And to keep the gradient stable across the entire 2.8T parameter model, they implemented a per-head muon optimizer.
Yes.
Instead of orthogonalizing the full projection matrices, which basically treats all the attention heads as one giant block, they applied the Newton-Schultz orthogonalization to each head's block separately.
Right, because orthogonalization helps maintain the independence of features, but doing it globally means heads with massive gradients drown out the updates for heads with very small gradients.
Ah, I see.
Applying it per head equalizes the update scales, ensuring every attention head learns efficiently.
Now, designing all of this math on paper is one thing. But if you walk into a data center and try to fit a 2.8T parameter model into physical GPU memory without leaving your silicon sitting idle, you run into the physical limits of hardware pretty quickly.
Oh, yeah, you do.
Let's talk about the system's infrastructure. Expert parallelism, or EP, routes tokens to different GPUs holding different experts. The problem is imbalanced token loads and dynamic shapes. The GPU constantly has to pause and tell the CPU how big the tensor is going to be for the next layer before it can even compute.
It's a huge bottleneck. So Kimi K3 implements a system called MoonEP to solve this. They mathematically proved that the maximum number of redundant experts needed to achieve perfect load balance is strictly bounded to E over R.
Wait, E over R?
Yeah, the total number of experts divided by the number of ranks.
Okay, so it's like managing reservations at a restaurant. If you have dynamic shapes, the kitchen constantly has to pause, count the guests, and change the recipe mid-service based on who actually showed up.
Exactly.
But with MoonEP, because they proved the bound is E over R, they just book the restaurant for exactly 50 people every single night. If only 40 real tokens show up, they fill the remaining 10 seats with mannequins, the redundant experts.
That's a great way to put it.
The shapes are perfectly static, meaning the GPU never has to talk to the CPU to adjust tensor sizes. The synchronization stalls drop to literally zero.
And that static shape guarantee enables zero-copy communication. But we also have to look at how they parallelize the 1 million token context window across multiple GPUs.
Right, because standard softmax attention requires you to swap constantly growing key value blocks across the network, which just chokes your bandwidth.
Yeah, so Kimi K3 uses KDA context parallelism, or KCP.
And because KDA is recurrent, I assume they just pass the fixed size recurrent state from one GPU to the next?
Well, the delta rule transition makes it a bit more complex than just passing a simple state. The effect of a local token sequence actually depends on the state coming into it. So KCP decomposes the transition locally.
How does that work?
Each rank computes a state as if it started from zero, alongside a cumulative transition matrix for its specific chunk. They exchange these fixed-size fragments via a single all-gather operation, and then each rank reconstructs its true incoming state mathematically.
Oh, that's clever.
Very. It allows compute to scale linearly up to 1 million tokens without saturating the network bandwidth.
And to squeeze even more out of the hardware, they use pipeline 02 to shard gradients out to the CPU. 02 normally shards optimizer states and gradients across the GPUs, right? But by pushing the gradient sharding completely to the CPU, they free up massive amounts of VRAM, specifically for those 1 million token contexts and the massive MoE activations.
Every megabyte counts.
Seriously. They also use a decoupled encoder process, literally hiding the vision encoder's forward and backward passes inside the pipeline bubbles of the text model.
Yeah, since the text model is waiting for data anyway, they just run the vision compute in the dead space.
That is just brilliant engineering. So pre-training establishes the foundation, but Kimi K3's high performance on reasoning, agentic tasks, and coding that stems from a massive test time scaling and reinforcement learning pipeline. They train 9 distinct expert models across 3 domains, general, agentic, and coding, and across 3 reasoning effort levels, low, high, and max. Then they consolidated all 9 back into Kimi K3 using multi-teacher on-policy distillation, or MOPD.
But running RL with 1 million token contexts is incredibly fragile.
I can imagine.
They rely on partial rollouts. They basically pause the trajectory generation when just a fraction of the rollout's complete, so they don't have to wait for the slow stragglers to finish before updating the model.
But the challenge with partial rollouts has to be the off-policy lag, right?
Definitely.
Like if an RL trajectory takes thousands of steps to finish and you pause it and resume it later, the underlying policy model has already been updated multiple times by the time that trajectory actually finishes.
Right.
So the data the trajectory is based on is totally stale. How does the math handle that extreme off-policy lag without collapsing the entire training run?
They handle it through strict per-token regularization. By mathematically constraining the policy updates within a localized neighborhood of the reference model, the algorithm inherently tolerates highly stale data.
Oh, so it puts a leash on it.
Exactly. It physically prevents the model from taking catastrophic update steps based on outdated trajectories. And to prevent out-of-memory errors during these massive multi-step generations, they utilize an external KV cache pool, writing idle prefixes back to CPU DRAM and only keeping the active decoding blocks on the GPU.
And the actual environments they use to train these agents are fascinating. They built Agent ENV, which is a custom micro VM-based sandbox using Firecracker.
Yeah, Firecracker's super lightweight.
Right. And it can pause, resume, fork, and snapshot entire operating systems instantly. You have agents running code, mounting disks, and executing multi-day simulated tasks like managing a complex HR workflow inside a mock Slack and mock Gmail environment.
Because they aren't just training on static question and answer datasets anymore, they're training a general autonomous loop. Hypothesize, act, observe the result, analyze the feedback, and adapt.
Right.
The Agent ENV infrastructure allows them to evaluate the actual final state of the operating system rather than just relying on the agent's self-reported text completion.
That is so cool. So when you combine 2.8T parameters, KDA, CTU, GLU bounds, and this massive agentic RL infrastructure, the benchmark results are wild.
Yeah, the numbers are great.
Kimi K3 trails Claude Fable 5 and GPT 5.6 Sol overall, but it dominates almost everything else. It hits 81.2% on Frontier SWE, 91.2% on BrowseComp, and 93.5% on GPQA Diamond.
Huge jumps for an open weights model.
And thanks to MXFP4 quantization of the MoME weights, it operates at a fraction of the serving cost of Fable 5. But I want to talk about the cybersecurity evaluations.
Oh yeah, those highlight exactly where the current frontier sits. At Tier 1, which is vulnerability discovery, it is incredibly strong. It found previously unknown 0 days in the Linux kernel, including a remotely triggerable heap out of bounds write and a dirty CCowW vulnerability in the RDMA subsystem.
That's slightly terrifying.
Yeah.
But at Tier 2, which requires executing end-to-end exploits on hardened targets, it struggles compared to human experts.
Yeah, the trajectory analysis showed that while the agent can exploit user space targets efficiently on hardened kernel targets, it gets stuck in these prolonged, unproductive debugging loops.
It gets tunnel vision.
Exactly. Or it finds the primitives but fails to string together the final exploit chain. It shows a clear remaining gap to human-level persistence, intuition, and long-term strategy selection.
Still, the engineering case studies in this paper are mind-blowing. The Kimi team used K3 to build Minitriton, a full GPU compiler with a custom Python front-end and PTX code generation. Then, in a 48-hour autonomous run, the model designed a functional inference chip, a nano-KPU, using open-source EDA tools. We are officially in the singularity Ouroboros.
The snake eating its own tail.
Exactly. We're using OpenWeight's AI models to write the GPU compilers and design the very inference chips that will be used to run the next generation of AI models.
It's crazy to think about, but pulling all of this together, the architectural elegance and the system-level efficiency of Kimi K3 is staggering. They've proven that test time scaling and complex RL can be successfully mapped onto highly sparse 3 trillion parameter OpenWeights models.
Which leaves us with a massive, somewhat provocative thought to close out this video. If models like Kimi K3 are matching this level of performance, the gap in raw model intelligence between open and proprietary labs is closing rapidly.
Very rapidly. The moat for proprietary AI labs isn't just having a smarter base model anymore. The moat is shifting entirely toward verifiable RL environment synthesis, like building platforms like Agent ENV at scale and extreme system-level GPU optimization.
Right, because if OpenWeight's models are already autonomously building their own custom GPU compilers and designing their own inference chips, how long until the open source community completely automates the AI systems engineering stack itself?
That's the real question.
If the AI can optimize its own infrastructure and route its own massive server clusters, the barrier to training the next frontier model drops to nothing but the cost of raw electricity.
It represents a fundamental shift in where the actual value lies in AI research moving forward.
Something for you to mull over while you look at your own cluster utilization metrics. Thank you for joining us for this session on AI Paper Slop. Keep reading, keep building, and we will see you on the next deep dive.